New information about 3I Atlas. NASA tests a new high-power space engine. Why is half the Milky Way hotter than the other? And in Space Bites Plus, different sources for 2 of Uranus's rings. All this and more in this week's Space Bites. So do you remember the interstellar object 3I Atlas? I know you have to sort of go way, way back, but there was this object that came through the solar system back last summer, and we were all excited. This was the 3rd interstellar object that anyone had ever seen, and all eyes, both on Earth and in space, turned to gaze at this object as it was passing through the solar system, made its closest approach to Mars, to the Sun, to Earth, and most recently to Jupiter. And now it is on its way out into interstellar space. I know it's easy to forget these things, how they consumed everybody's attention, and there was all this speculation, and now all that's over because now we're just waiting for the new hotness, the next interstellar object. But just like, let's just stop and just remember 3I Atlas. Well, here are 2 more interesting things to learn about 3I Atlas. So the first is observations made by James Webb. And we got a lot of observations from it pretty much within the month or so after it had been discovered. And we found that it had high amounts of carbon dioxide, but one of the things that seemed to be missing was high amounts of methane, which can be common in various comets. Well, after it completed its closest approach to the sun, it started to kind of break apart this outer shell that had been hardened onto it for its billions of year journey through the Milky Way. And we saw large amounts of methane start to be emitted by the comet. And this is great because this is telling you more about the internal structure of 3I Atlas. And we know that it was rich in methane. We also got observations that came from the Atacama Large Millimeter Submillimeter Array, which is a radio telescope. And ALMA is able to observe the comet when it was very close to the sun. That's a very difficult observation to make for an optical telescope because you have to look in the daytime. But radio telescopes can look during the day and be able to even then observe objects in the sky. ALMA was looking for the ratio of water to something called deuterated water, which is essentially, you've got the water, one of the hydrogen atoms has an extra neutron in it, and that's deuterium. And so they were looking for this ratio, and this ratio has been well measured here in the solar system. Typically, it's about 10,000 to 1, but in 3I Atlas, they found that it was about 30 times higher than what we see in solar system comets, and about 40 times higher than the ratio that we find in the Earth's oceans. And what that means is that 3I Atlas must have formed in a very cold environment, colder than negative 243 Celsius. And this is great. I mean, these are the kinds of discoveries that we're really hoping to find, where you would watch this comet from different instruments, different wavelengths, and you would see different kinds of molecules, ratios compared to what we see in the solar system. And that because we have learned so much about the early solar system and how comets play a role and tell us about the sort of earliest stages of our own solar system, we're now able to then compare and give you a sense of what star system 3I Atlas formed in. And I think, we're starting to see this kind of research start to come out now. And I think over the years, as astronomers continue to crunch the data, we will learn more about just the star system that 3I Atlas formed in. We may not ever know where it came from, but we'll learn some of its characteristics. We've got a story about this from Matt Williams. NASA has tested out a new electromagnetic thruster that runs on lithium metal vapor. Now, we have ion engines on various spacecraft. There was the Dawn mission, and right now there's the Psyche mission, where you use solar power to accelerate ions out the back of the spacecraft. These are great because they are very long running, they're very efficient, and they can accelerate a spacecraft to really high velocities over long periods of time. These ion engines can run for months, even years, just continuously building up the velocity of the spacecraft. But the thrust is pathetic. I always describe it, you could hold a piece of paper in your hand And the weight that you feel of the piece of paper is the amount of thrust that this spacecraft is going to be providing. And that is not enough for the kinds of missions that we might want to do. Say ones with humans, sending humans to Mars. We need a lot more thrust. And so NASA tested out this new electromagnetic thruster. It's a type of technology called a magnetoplasma dynamic thruster, an MPD. And this technology has been in development at NASA since the 1960s. They've known how to do it. It just requires tons and tons of energy. And so they ran this test on this new setup, and they were able to get thrust levels that are about 25 times higher than what is seen with the ion engine on Psyche. So imagine 25 pieces of paper on your hand. Still not very much. But they're hoping to reach power levels between 500 kilowatts and a megawatt per thruster. And you could have some mission to Mars, for example, that's carrying humans on board, and you might have a whole collection of thrusters. And when you have them all together, you might have, say, 2 to 4 megawatts of power that's coming out of this ion engine. And now you're getting some serious thrust, but you're going to need some kind of high power, like electricity source, like a fission reactor on board your spacecraft. And so you can imagine if this thruster continues to be developed, goes to space, bolted together with a nuclear reactor, that we could see fast flight times or large amounts of cargo being able to go to distant places like Mars. And we saw this new NASA Ignition initiative where they're proposing to take the propulsion module from the Deep Space Gateway and use that as a spacecraft and to carry a bunch of helicopters to Mars, the Skyfall mission. And so we're seeing tests of the kind of thrusters that might be used with that mission. If you remember a couple of weeks ago, I sadly informed you that the White House had made its budget request for NASA, and they were looking for very steep cuts from the NASA budget, about 25% to NASA's total budget, about 50+% cuts to NASA science. But I also held out a glimmer of hope that Congress would overturn that budget. And last year it took a while for Congress to decide that they were going to stick with the regular NASA funding. This time around, they acted very quickly. We got a House Appropriations Subcommittee this week. They've advanced a spending bill that will keep NASA at 2026 funding levels. So just shy of $25 billion, exactly what they had last year. Now, they're looking to push a little bit more, about an extra billion, into space exploration and take away about $1 billion from science. So we're going to see a little bit of shuffling of money from science to exploration, but still it's not the dramatic cuts that we had seen that the White House had originally wanted to do. So good news. One of the unfolding mysteries of the cosmos is how we got supermassive black holes here in the universe so early. We've reported on supermassive black holes with hundreds of millions, even more than 1 billion times the mass of the sun, seen within the first billion or so years of the age of the cosmos. And when you try to figure out the ways that you could get those supermassive black holes, it's really tricky to do. You can imagine you have a big cloud of gas, collapses down, you get a star, the star explodes, you have a black hole, that black hole finds another black hole, those black holes merge, the black holes are able to feed on the surrounding material, and when you run that math, you don't get the mass of the black holes that astronomers have found so far. So there needs to be some other mechanism. And the main view for this mechanism is some combination of a direct collapse black hole and mechanisms that can feed black holes more efficiently than what they would normally do under the conditions as we understand them. So researchers have proposed that maybe decaying dark matter could give the kind of energy that would kick gas clouds into collapsing more quickly. So there's this proposed type of dark matter particle called the axion. And, we don't know if the axions exist yet, but if they do exist, one prediction is that these particles will decay. And when they do decay, they will release energy. And it doesn't have to be very much energy, but the right amount of energy at the right place put into gas clouds could act as the seeds that would cause those gas clouds to collapse more rapidly than what you would expect under normal conditions. And so researchers are proposing that if dark matter is made of axions, then those axions could have contributed, essentially forced clouds of gas to begin collapsing early on and could help drive those more massive, supermassive black holes. We got a story about this from Carolyn Collins Peterson. Every week we do a vote on our channel where you tell us what you thought was the best space news story of the week. And the winner last week was that the Nancy Grace Roman telescope is under budget and ahead of schedule. So thank you everyone who voted. Now, of course, we will put the vote to this week's episode into the post tab here on our channel. So if you want, go to the post tab. You should see the vote right there. But also subscribe to our channel, click on the notifications bell, train the algorithm, and be trained by the algorithm. So the Milky Way is a vast collection of stars, and then it is surrounded by this halo of gas. And the gas is extremely hot. It can be 2 million degrees. Now, it's also very diffuse. And so even if you were passing through this hot halo of gas around you, you wouldn't experience boiling temperatures. But it turns out that this halo isn't the same temperature. It's a little bit hotter on the southern side of the halo than it is on the northern side. It's about 12% hotter in the Milky Way's southern hemisphere gas halo. This is a mystery that has been puzzling astronomers for a few decades. And now astronomers think they've found the answer, and that is the Large Magellanic Cloud. So what's happening is that, of course, the Large Magellanic Cloud is much less massive than the Milky Way, and so it is a satellite galaxy of the Milky Way. But the Large Magellanic Cloud does have some gravity of its own, and so it is pulling on the Milky Way, causing the Milky Way to get closer to the Large Magellanic Cloud. That is causing the gas on the side that is facing the Large Magellanic Cloud to compress, and the side that is on the other side to become less dense. And if you've ever put air into an inner tube and you feel how the temperature of the inner tube rises because it's like a piston that is compressing the gas together and increasing the temperature. And this is the explanation for why the Milky Way has this hotter part of its gas halo compared to the cooler part. Got a story about this from Mark Thompson. Where does the Milky Way begin and end? Now, we've got all of the stars in the Milky Way. We've got that halo of gas that we talked about earlier in this episode. There's an even larger halo of dark matter that surrounds the Milky Way and extends out to almost touch, or maybe even overlaps with the halo that is around Andromeda, which is on its way towards us. So you've got to come up with some kind of line. Where would you define the line for where the Milky Way begins and ends? It's very similar to, like, where does the solar system begin and end? Is it the planets? Is it the Kuiper Belt? Is it the Oort cloud? Is it the gravitational influence of the solar system? Is it the heliosphere? So astronomers have analyzed the stars in the Milky Way, and in a paper, astronomers said, well, let's mark the edge of the Milky Way where the star formation can no longer happen. They used a bunch of surveys of the cosmos. They used Gaia, which is great, and gathered information on about 100,000 giant stars. And they tried to track where the star formation has been happening in the Milky Way. You can look at the age of the stars to tell you how long ago it formed. They're able to measure where this active star formation has been happening in the Milky Way. And they found that if you sort of measure from the center of the Milky Way out to this outer edge, it's about 40,000 light years away from the center of the Milky Way. And then you do have stars out beyond that 40,000 light years. When we talk about the size of the Milky Way, we often say it's about 120,000 light years across, but that a lot of the stars in that outer region are migrants, that they have been kicked out into this outer ring outside of the Milky Way through interactions with other stars. But the stars that are actually being born in place in the spiral arms and the various regions of star formation, that only gets you out to about 40,000 light years away from the center of the Milky Way. So by one definition, the Milky Way is about 80,000 light years across. We've got a story about this from Andy Thomaswick. We know of over 6,000 confirmed exoplanets now, with probably another 10,000 candidates that still have to be follow-up studied. But the main method for finding exoplanets is using the transit method. This is where you look at the star and you watch the telltale signature of something passing between us and the star, a planet. And it was sort of thought that this process was like clockwork, that you could watch the star, the planets would pass in front of the star, and you would expect that, year after year after year. But now astronomers have found an example of an exoplanet where it would have only been possible for us to see transits within the last 200 years or so. And soon we will no longer be able to see transits and have to wait another 10,000 years for the planets to start transiting again. So the system is called TOI 201. TOI, that is the TESS object of interest. So it was discovered by NASA's TESS satellite. And it's an F-type star that's 371 light years away from Earth. It has 3 exoplanets that are orbiting around it. One takes 5.8 days to go around. One takes 53 days. And the last one takes 2,900 days to go in orbit. And that last one has this highly elliptical orbit. So it's much more comet-like than sort of circular planet-like. And as this planet makes its motions around, it changes the orbits of the inner planets. And you get this oscillation of the entire system that then rotates it from our perspective. What's interesting is that we know of other examples where you have planets that are orbiting their stars on these elliptical orbits. And it might be that it's just a fluke that we are able to see the planets right now, and that in the future, we will no longer be able to see those planets. And then it means that we're probably gonna have to go back and reanalyze other stars where we didn't find any planets before, because planets might start appearing if the orbits are interacting with these giant elliptical orbits. Got a story about this from Lawrence Tugnani. We owe a lot of the Earth's habitability to the moon. It has stabilized the climate. It has kept our axial tilt where it should be. It has encouraged life to go from the seas to the land. So it makes sense for us to search for other Earths and their moons out there in the universe. That it might be that maybe having a large moon is one of the necessary steps for a planet to be habitable. And so far, in mid-2026, we have no examples of exomoons discovered so far. And astronomers thought they had found an example of an exomoon. So the star is called TOI 700. It's about 100 light years from Earth. Again, another planet discovered by TESS. And it's a small red dwarf. It has multiple planets orbiting around of it, 2 Earth-sized ones within the habitable zone. And based on the size of the planet and the size of the star, the difference in brightness between the star and its planets meant that astronomers figured they could use the coronagraph on board James Webb to distinguish the movements of the planet and try to detect the presence of a moon going around the planet. They found a really interesting oscillation that was going on around the planet, but it turns out this was contamination from the star, that there are these stellar granulations on the surface of the star that was mimicking the light that might have been coming from a moon.
That's no moon.
And this is a big problem. And this is something we've talked about in the past, that you're getting this contamination from the star. This is why astronomers are having a really hard time measuring the atmosphere of the planets in the TRAPPIST-1 system. But the astronomers are very confident that if you can come up with some kind of algorithm to remove this contamination of this granulation data from the star, that the combo of James Webb with its coronagraph is sensitive enough to find exomoons around this planet. So they haven't been found so far, again, but the problem seems to be kind of well understood at this point. And now hopefully it's just a matter of time before astronomers are able to come up with a methodology to confirm moons out there. We've got a story about this from Andy Thomaswick. Hope you're enjoying this week's episode of Space Bites, but I've got to assume that if you're watching this on YouTube, you saw an ad, and you might also see an ad at the end of this episode. Now, we remove all of the ads from the middle of the episode because YouTube lets us, but we can't remove them from the beginning of the episode. But we think there's a much better place for you to watch Space Bites, and that's over on Patreon. We put every episode on Patreon. We make it ad-free, and to encourage you to check out our content over on Patreon, we put an additional story into every episode. Now, you don't have to join our Patreon. You don't have to become a member. You don't have to give us any money. You can watch it totally for free and get no ads. And I'm going to put a link down in the show notes so you can go watch that episode and then get into the habit of watching our stuff over on Patreon instead of just here on YouTube, unless you love ads. And this week's bonus story is the strange source of 2 of Uranus's rings. And of course, this is just a fraction of all of the stories that we're working on at Universe Today. And this week is a monster week. I have been writing my weekly email newsletter for hours and hours and hours because there are so many stories this week and a lot of really cool ones. And so if you want like just a breakdown of every single interesting space news story that is happening this week, you should definitely check out my weekly email newsletter. I send it every Friday. It's completely free. There's no ads. You can subscribe. Go to universitytoday.com/newsletter. Have you made something cool with Rubin data? I'd like to hear about it. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barry Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bielak, Dark Finger, David Gilton, David Matz, Evan Lindstrom, Evan.pro, James Clark, Janice Smith, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Switz, Michael Purcell, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Rain Kaidu, Richard Williams, Sean Sargent, Stephen Fallon Munley, Team 49, Telescopes Canada, Vlad Shiplin, Wolfgang Klutz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. I got a comment on Patreon from Galactician who says, I started paying Rubin data and I'm building a viewer online for the things that I'm interested in. I never would have thought to do that without this channel. Thanks, Fraser and the team. So this is great. This is exciting. This is something that I've been trying to get this message out to the audience. People keep asking me, like, when are they going to release the information on Rubin? They are releasing the information. There are a bunch of different data brokers. They are grabbing this fire hose of data that is coming from Rubin. They are organizing it in ways that are relevant to their community, whether it's extragalactic stuff, whether it's stuff in the solar system, and they're making this available to anyone who wants to use this to then make discoveries. You've got this API of the information, and you just have to program something that will allow you to sort, scan, download, and analyze this data. You could probably hook up a way where you can have it tell you every time that there is a supernova of a higher brightness than 12, and then you can automatically point your telescope to do fallen observations of that supernova. You could have one of these systems help you find new comets or new asteroids in the solar system. Maybe you could be there and ready to observe Planet 9 when it's first found. And before the age of these large language models, coding agents, it was a really hard, like, you had to be a programmer. And so if you were a programmer, then this would be the kind of thing that you could do. But now we live in this world where even if you don't know what you're doing, you can ask Claude or ChatGPT to help you develop some kind of interface, some kind of viewer for Rubin data that you can use for some purpose. And I just want to encourage you, all the people who are working on this kind of thing, please let me know. Post in the comments, drop me an email, let me know the projects that you're working on, and I will try to highlight some of them in future videos just to encourage people to go and do this. There's nothing stopping you at this point. You don't have to ask for permission. These APIs are ready to go. The coding tools are ready to help you build things. It's really up to your imagination. What useful things could you do to showcase this data coming from Rubin? So good luck. Let me know what you find.